some people filtering in, we'll get started. There's still, I believe, 3 people that need to finish their quiz. So I'm not going to give away a ton here, but I think some of the people that need to finish the quiz are still not on with us. So hopefully you got a chance to take a look at your score and my comments. Again, all the reason more for completing work within Google Docs. Google Docs. Go to a specific question, look at your answer and comment on it. So I think one of the toughest questions continues to be, or 2 of the toughest questions continue to be these 2 right here. The relationship between air temperature and air's ability to hold vapor. And then question number 4, why cooler air typically has a higher relative humidity. So we're going to see this again because we'll probably have one final test by the end of the year. We'll wind down with weather and have one final test. Just for your information, if you want to go back into your quiz and make a note about any of these, if you got these 2 wrong or one of these 2 wrong, question number 3 is really asking you to go back to graph number 1 that we built, where we saw a linear relationship between air temperature and air's ability to hold vapor. In other words, higher temperature, more ability to hold vapor, and vice versa. Question number 4, a lot of us are doing an okay job of saying it's the cooler air that typically has a higher relative humidity. And we can see that when we look at graph number 2 that we did in Do the Do. But a lot of us are still struggling to come up with a good explanation. And so on a lot of your quizzes, I just typed a comment that was open-ended with a blank to fill in, and it looked something like this. What would we put in that blank? Anybody out there unmute your mic and put in this blank? There's several different words we could use.
Hold vapor.
A couple of you said something at the same time, so it wasn't very clear. Try that one more time. What's true of cold air? It's easier to what?
Hold vapor.
No.
It's easier to become fully saturated.
Yeah, it's the simple thing that we need to know about cold air is that because it doesn't hold as much vapor, it's easier to soak. It's easier to saturate. It's easier to fill up. And so we got to go back to the demo from going on 2 weeks ago now, where I filled up a small glass and it was soaked, and then I put that same amount of water into larger and larger and larger glasses, meaning that air, when we warm it up, is harder and harder and harder to soak because it can hold more. So some things to consider for the weather quiz. If there's anybody who has questions right now because we're on it, please feel free to ask. Otherwise, a couple of you, Tate, Will, Maddox, get your videos back up, please. We're going to move into brand new stuff on static electricity. Are there any questions? All right, so I'm going to transition. Feel free to type questions if they come up. or you can ask now. Where are my notes here? Okay. So hopefully some of you got to see this document here. I posted this, or I actually added a link to this document probably 8:30 this morning. So after I initially posted the link to today's Google document. But what are we looking at on this picture? What do we have a picture of?
Atom.
Yeah, it's a poorly drawn atom, but it's meant to be an atom, an individual atom. And in a moment here, we can maybe try and figure out which atom it is, or what it's an atom of. But there's a couple things that I want you to know. Now, if you have this document open in front of you on a screen, that's great. If you were able to get it printed, that's really great. If you don't have it open and you're left to drawing, then let's get going with that drawing right now. Colors don't mean a ton, but it's just going to help us to stay organized. So why don't we start out actually with these red circles and these blue circles in the center. That looks good right there. So what I've attempted to try and show you here is that I've drawn 1, 2, 3, 4, 5 red circles and 1, 2, 3, 4, 5 blue circles. And those are in the center of the atom, and we call that the nucleus. N-U-C-L-E-U-S, the nucleus of the atom is made up of these red neutral neutrons and these blue positive protons. So when we talk about an individual atom, there's fundamental parts in terms of energy that they're made up of. And this word right here is a little bit difficult to see. This word says mass, M-A-S-S. The entire mass of an individual atom is made up of the protons and the neutrons in the nucleus. Questions on what you're seeing so far? There's a couple other things I want to point out. Underneath the word neutron, I have a 0, and underneath the word proton, it's a little bit hard to see, but I have a positive or a plus symbol. What do those symbols refer to? What could we say about a neutron or a proton?
A neutron doesn't have a charge, and a proton has a positive charge, and an electron has a negative charge.
Okay, we'll keep it to the neutron and the proton for now. If you're taking notes at home on paper, we would just want to maybe add this idea that a neutron has no charge. 0 charge, not positive, not negative. It's just a subatomic particle that has some mass. And a proton, so we can maybe do a little memory trick here that P positive proton so protons have positive charges. We just got to be careful because a lot of people like to say, oh, okay, N negative neutron. No, neutral neutron. And then the other thing that I've done here is I've written the word identity underneath the word proton. Protons are the subatomic particles that give atoms their identity. So if you were to say, let's have a look at a periodic table. And I look at a picture of the periodic table and I look for number 5. I had 5 protons in my drawing. 1, 2, 3, 4, 5. So the drawing in our notes is actually an atom of boron. B boron is number 5 up here. That means it has 5 protons. And you don't have to worry about that too much. We're going to get into the structure of the atom more next year. But understanding the basics of how an individual atom works is helpful for understanding static electricity. So are there any questions on what we've drawn on this right side here with the nucleus? Any questions with what you're putting on paper or seeing in front of you? Then we're going to transition over to the left-hand side. And Caleb already gave this, but what I've attempted to draw here are some orbits, kind of like the way the Earth orbits around the sun, and these little black dots are our electrons, and they carry a negative charge.
Can't the electrons, like, they can be in like a field of like wherever? Aren't they like not in a specific orbit though?
Right, right.
Okay.
So Braden, you asked a question about this document. This is on today's Google document. There's a link to it, so you should be able to print it. Good question. And then I do want to get to what Will just brought up. So a couple things about this drawing. First of all, this is overly simplified. This is just a basic look at an atom, and really it's not accurate in a couple of ways. I don't want to get too lost in the weeds about atomic structure and subatomic particles, but the thing you do need to know is that the nucleus of an atom, where all the mass is incredibly small. And where the electrons are around the nucleus, it's incredibly big. So we could kind of, there's an analogy out there that says something like, if you, can I have somebody's got their mic unmuted. Everybody make sure you're, thank you. There's an analogy that we could picture that if we say, if we're at a big stadium, picture a big stadium that you've been to. If you've been to Washington Grizzly Stadium, or if you've been in the Adams Center or something like that. If we were to picture that big stadium as an atom, we would say the nucleus is roughly the size of a marble, and we're going to put that down at the very center of the field or the center of the court, and that's where all of the mass is. It's all of this mass densely packed into this tiny little thing, and then the electrons would be way out in the nosebleed seats, way far away. So we get to this idea that an atom really is just a bunch of empty space between the nucleus and where the electrons are. And then as Will brought up, electrons don't confine themselves to these nice, neat orbits. This is not an accurate depiction, but for our purposes today and just keeping things simple, you can think of it in terms of orbits if you'd like. More accurate would be to say that electrons have energy levels that they exist in, and it gets really complicated with distance away from the nucleus and the shape of the energy field that they exist in. But all I want you to know for today is that we have electrons that are outside and they have a negative charge. They kind of define the volume of the atom. And then on the inside, we have the nucleus where we have positive charges and neutral charges, and they make up all the ass of the matter. I just said a swear word, and it's been recorded. But they say ass in the Bible. Oh, I said it again. All the mass of the atom. See, I got Elise. Elise is laughing. Okay. This is a really good test, and who's paying attention? Okay, I think Braden's laughing. This is very good. All right. Welcome to science, kids. What was I saying? Mass of the atom is in the nucleus. All right, let me ask you this question. Collect myself. If we were able to influence anything about the atom, like affect it somehow, if we were able to add or remove charges, what would be the easiest to influence? The electrons, the neutrons, or the protons? What do we think?
Electrons.
Anybody think differently other than Caleb?
The neutrons.
Okay. Anybody else? Would anybody think protons? Well, here's what I'll say. I'll side with Caleb because the neutrons and the protons in the nucleus are really, really densely compact together. Meanwhile, the electrons are way out in these energy levels. So the simple understanding I want you to take away is that since the electrons are way out here, we can add or remove electrons. And this allows us to build up a static charge. So I want to demonstrate this because I'm going to ask you to do the same. There are hundreds of ways to demonstrate static electricity, and I'm just going to show you one. Can you see the aluminum can there? Good. And I've got this plastic tube. For whatever reason, plastic is really good to work with when we try to demonstrate static electricity. And then the other ingredient I have over here are my hunting pants that are made out of wool. Wool, for whatever reason, works really well for taking charge off of this plastic. So if I rub this plastic tube through the wool, what am I doing to the tube and what am I doing to the wool? What do we think based on what we just put into our notes? Somebody besides Caleb, somebody besides Will, somebody else. What am I doing to this? What am I taking away from this plastic tube?
You're taking away the protons?
Well, I can't influence the protons because the protons are stuck in here.
The electrons?
Okay, so I am taking electrons off of this tube. So all of the tiny little individual atoms on this tube have electrons on the outside. I rub the wool, I take electrons off of the tube, and I put them onto the wool. So how does the tube become charged? If I remove electrons from the tube, how does it become charged? Somebody besides Tim or McKinley?
It has a positive charge.
Okay, if we take negatives away from this thing, it becomes positive. If I add negatives to this, it becomes negative. So we can essentially say that by rubbing this plastic tube on the wool, I charge this thing positive, this becomes negative. Now the can, I haven't done anything to. So there's one more word I want to introduce you to, but I want you to see this demo real quick. So I'm going to lay the can on its side. It just sits there. Can you see it? And I'm going to charge this up one more time. Notice how I like to just move this tube in one direction, like my favorite band. Off the edge of the table it goes. Want to see it again? Can you see it? There's the tube. Not touching it, by the way. Pretty cool, huh? So, in your notes, I want you to scroll down and I want to take a look at this final word here. Now, this is one that I'm sure you've all seen where it's just like we said, plastic tube becomes positively charged. There was the wool. It accumulates some negative charges. If I would have brought this plastic tube next to somebody's hair, especially somebody that has really dry, straight hair, you've seen this before probably where their hair stands up. I didn't do anything to that person's hair. I didn't do anything to the can. So this is a word that I want you to be comfortable using. When you bring that charged tube next to some object and you get a reaction, the thing like the hair or the can, we polarize it, which means that we repel the like charges and we attract the opposite charges, so we get something to occur, like the can rolling off the table or somebody's hair sticking up. This is static electricity at work, and this is how lightning works, just on a grand scale. So, questions on the demo? Questions on where our charges occur? Questions on the word polarization? The green blob. Let me see what my green blob says. That says wool. Is that what you were referring to, Carson? That was my piece of wool. This is my plastic tube. I didn't draw a can because I used to do this with somebody's head with dry, straight hair. Let me just go back to our document that was posted for today. So we will not meet anymore this week. We don't have any more live lessons for the week. So I just want to send you forth today by taking a look at what I wrote in our document. Here we go. And this is something that I'll have set to go for Monday, but Monday we're going to plan on doing a Zoom lesson, but we're going to break out into different rooms where you'll have 2 or 3 other people to share a demo with. You're going to be in charge of demonstrating static electricity in some way, similar to what I just did. If you do a Google search or a YouTube search, you'll find hundreds of examples. So I'm just going to go with the assumption that there will be some repeat examples, but if I break you up into different breakout rooms, hopefully the other person or the 2 other people in the room have different demonstrations. You're going to be in charge of demonstrating one, and I want you to tell me where positive charges build up, where negative charges build up, and I want you to use the word polarization. So similar to what we just saw and what we have in our notes, when I rub the wool on the tube, the wool takes off electrons, so I would say the wool becomes negatively charged. The tube becomes positively charged, it had some electrons removed, and then whatever I bring this tube next to becomes polarized, where I repelled the like charges, and you've heard this idea before that opposites attract. And that really comes from the world of science. Questions? So what you'll do in terms of submitting work for this is on Monday we'll demonstrate it. I'll ask you to have a visual, whether that's, it can be as simple as a piece of paper that you can show your classmates that you're in the same breakout room as, how your demo works, and then that's the thing that you'll submit to me. just a picture. You can do a Google Doc. You don't have to get all fancy with a huge poster or anything like that. But that's the gist of it for today. If there are no questions, you are free to go. Some of you do still need to do or redo the static electricity video and Edmodo quiz. And then, like I said, I still need the weather quiz from Monday from 3 of you. That's it for today, 7th graders. Be in touch with questions.
Bye, everyone.
Mr. Crockett.
Hasta la vista.
Jack and Braden, hang out if you can.
Mm-hmm.
Jack, can you turn your video on? Remy, I think you still have to do the Edmodo video quiz, right? Oh, Jack's gone. Braden, what's the word on the quiz?